Hi, everybody. Thanks for tuning in. My name is Dylan Amaya. I'm a research scientist at the NOAA Physical Sciences Laboratory in Boulder, Colorado, and I'm excited to share some of our new research thinking about how air-sea coupling shaped North American hydroclimate and its response to different ice sheet characteristics during the last glacial maximum. I quickly want to shout out my different co-authors on this work. There's Alan Seltzer, who's at Hui, Chris Karnauskas at CU Boulder, Juan Laura at Yale, Sally Zong at Johns Hopkins, and Pedro Denizio, who's also at CU Boulder. I also want to take a quick second to mention that we have some postdoc funding to follow up on different aspects of this work. So if you watch this presentation and you are interested in thinking about these problems further, feel free to email me for details on that job opportunity. So just jumping right into it here, we all probably have a pretty good idea of what modern day hydroclimate looks like along the American West Coast. Mostly that the Pacific Northwest is very moist, there's lots of rainfall, and the American Southwest or the US Southwest by comparison is much drier. And the reason for that is the North Pacific atmospheric circulation is set up in such a way that the storm tracks are preferentially driven to the Pacific Northwest. These tongues of moisture coming from the tropics, these atmospheric rivers, are driven by the North Pacific jet stream preferentially to the Pacific Northwest. But we know from past proxy reconstructions of past hydroclimatic change that has not always been the case. For example, if we look at this figure from Oster et al. 2015, you can see that different proxy reconstructions show that the American Southwest was much wetter than it is today, and the Pacific Northwest, by comparison, was much drier than it is today. And for as long as we've had these different proxy reconstructions, we've been asking the question, why? You know, what was it about the LGM climate system that was so different that led to this drastic reorganization of hydroclimate throughout the North American West Coast? And the longest standing hypothesis for why this has been this idea that the Laurentide ice sheet, which sat over North American continent, was very tall. It was about 3 kilometers tall, and it acted sort of as a rock in a stream. You know, it was deflecting the jet stream both north and southward in such a way that the storm tracks were also shifted with it. That steering flow shifted the storm tracks southward, driving much more of that rainfall to the U.S. Southwest and much less of it to the Pacific Northwest. So it is this mechanical influence from having a massive barrier in the way, blocking the mid-latitude westerlies, pushing these storm tracks further south. But we have some new tools and some new insight that we'd like to use to revisit this question. So that's one of the major research questions that we want to address here. Can we isolate the mechanical and thermodynamic influence of continental ice sheets on West Coast hydroclimate? In particular, can we isolate the influence of these different ice sheet characteristics on the North Pacific jet stream and its downstream influence on rainfall over the North American continent? Also, we would like to think about how air-sea interactions and ocean dynamics might be modulating these overall responses to these different ice sheet characteristics. And the way we're going to do that is by looking at a suite of Community Earth System Model version 1.2 simulations that were actually run by Pedro Denizio et al. In 2018. So if you're interested in more of the gory details behind these different simulations, I'll just refer you back to this paper. But for the purposes of today, I'm just going to show you the results from 3 of their simulations. They have a LGM full experiment, which is just a climate model experiment that has the major boundary conditions set to LGM levels following the PMIP3 protocols. And we can compare this LGM full experiment to 2 different single forcing experiments. We have what we call a White Mountain experiment, where the climate model is forced only with the ice sheet characteristics from the LGM. So we have ice sheets that are both very tall, so we have the topographical effects of the LGM, and they're also very bright, so they have the surface characteristics of the LGM, and we call this a White Mountain. So this will isolate for us the mechanical plus the thermodynamic influence of ice sheets on the large-scale climate system. We can compare these simulations to a Green Mountain experiment, which is only forced at the boundary by the topographical influence of the ice sheet, but we set the surface characteristics of this ice sheet back to pre-industrial levels. So this ice sheet is very tall, but it's not very bright. So it doesn't have those thermodynamic impacts on the climate system. It only has the mechanical influence on the climate system. And I should also mention that we also have a pre-industrial control simulation that we're comparing to each of these simulations to give us our anomalies that you're going to be seeing. In addition to these different experiments, we actually reran the White Mountain, Green Mountain, and pre-industrial control simulation using 3 different ocean model configurations, and we did this to isolate the impact of air-sea interactions and ocean dynamics in modulating the overall response to these different boundary conditions that you see in the White Mountain and Green Mountain experiments. So first off, we have your classic AMIP experiment. It's an AGCM-only experiment where the surface SSTs are set to the climatological values from the pre-industrial control simulation, And in this case, you're just seeing the direct atmospheric response to the changed boundary conditions that are set to LGM values. So in the case of the White Mountain, it's that direct atmospheric response to both mechanical and thermodynamic forcing from the LGM ice sheets. And in the case of the Green Mountain, you're getting the direct atmospheric response to mechanical forcing from the ice sheets. We can compare that to a slab ocean model case. So in this case, we're coupling our atmospheric model to a very thin slab ocean. It's about 50 meters deep everywhere. It's non-time varying. And in this case, you can get air-sea heat exchange between the ocean and the atmosphere. So you get some sort of air-sea coupling. You can get air-sea feedbacks like wind evaporation SST feedback, for example, or low cloud SST feedback. But there are no ocean dynamics to push heat around within the interior of the ocean. And then we can compare that further to our dynamical ocean model case, where we have an atmospheric model coupled to a fully dynamical ocean model. And this is your fully coupled climate model with western boundary currents, ocean advection, and AMOC. And in each case, all three of these have been appropriately spun up. They're all in equilibrium with top of the atmosphere radiative forcing. All right, so let's jump into the results here. We're going to start by looking at the North Pacific climate response to our LGM full case. So this is the full LGM climate simulation. And what you're seeing here are wintertime averaged atmospheric circulation anomalies in that LGM full simulation. So the top left is showing you zonal wind anomalies at 500 millibars. That's in shading. And the contours are showing you the climatological position of the North Pacific jet. So we see a deceleration of the westerlies on the northern flank of the jet and an acceleration of the westerlies on the southern flank of the jet. So taken together, that would imply a southward shift in the North Pacific jet stream, which leads to a north-south dipole in precipitation along the North American west coast in our model simulation. So we get a moistening of the American Southwest and a drying of the Pacific Northwest. And this north-south shift in hydroclimate actually matches the proxy reconstructions really well, which you can see here as these circles. And our model simulation actually compares very well with the ensemble mean from the PMIT-3 archive. So these are the same anomalies in that ensemble mean. So this just gives us confidence that our model is doing something sensible. It's not an outlier relative to either the proxy estimates or past climate model simulations forced with similar boundary conditions. So now we're going to compare to a much simpler case and see how much of that full climate response to different LGM boundary conditions can be explained by mechanical forcing from the ice sheet topography alone. We'll begin by comparing to our Green Mountain AGCM only simulation. This is, again, an atmospheric model that is uncoupled from the ocean. There are no air-sea interactions. There are no ocean dynamics. So this is just the pure atmospheric response to mechanical forcing from the topography of the ice sheet. We see a very similar southward shift in the North Pacific jet stream when compared to the LGM full simulation that you saw on the previous slide. And that leads to a very similar north-south dipole in West Coast hydroclimate. We get a wetter American Southwest and a drier Pacific Northwest. And if this is all the information we had, then we might reach the same conclusion that previous studies have, that mechanical forcing alone from the ice sheet is enough to explain LGM hydroclimatic change that we see in proxy reconstructions. But what I think we'll see here in a second is that we might be arriving at the right answer, but for the wrong reasons. And we see that as soon as we start to couple our atmospheric model in our Green Mountain simulation to a realistic ocean, and we allow for realistic air-sea interactions and realistic ocean dynamics. And basically what we see is that the atmospheric circulation anomalies in this Green Mountain slab ocean experiment and in the Green Mountain dynamical ocean model experiment shows a broad deceleration of the westerlies throughout the North Pacific, which leads to basically the opposite hydroclimatic response along the North American west coast. We get a drier American Southwest and a relatively wetter Pacific Northwest. So something about air-sea interactions is overwhelming this tendency for a mechanically forced southward shift in the jet stream and giving you a completely different response. So this sort of suggests that mechanical forcing alone from the topography of the ice sheet is not enough to explain our full LGM simulation response, as well as our expectations from proxy reconstruction estimates. So now let's make things a little bit more complicated by adding the additional thermodynamic forcing from ice sheet albedo and see if that gets us closer to the right answer. In our White Mountain AGCM simulation, you see a very similar southward shift in the North Pacific jet, and once again that north-south dipole in west coast precipitation. And you'll notice that these maps look very similar to the Green Mountain AGCM simulation, and that basically says that the additional thermodynamic forcing that we got from the albedo of the ice sheet in the White Mountain AGCM simulation, it didn't change anything. So in this uncoupled world, in our AGCM uncoupled world, mechanical forcing really is driving the vast majority of the large-scale climate response to the different boundary conditions. However, the addition of the thermodynamic forcing does matter a lot more when we start to include different kinds of air-sea coupling. For example, when you look at our White Mountain Slab Ocean model simulation or our White Mountain Dynamical Ocean model simulation, you see a very clear southward shift in the North Pacific jet and a very clear north-south dipole in West Coast hydroclimate. And you can see how different these are compared to our Green Mountain coupled simulations, suggesting that the coupled climate response to direct thermodynamic forcing from the ice sheet is very important to getting something that looks much closer to the realistic LGM full simulation, which of course is that fully coupled climate system as well. And one other thing I want to point out is how similar the slab ocean model and dynamical ocean model results are in all of our simulations. And this suggests that dynamical ocean processes are sort of a second order control on the large scale atmospheric response to these different boundary conditions. Really, it's air-sea coupling that is driving the bulk of the response. So that was a lot, but I just very quickly want to summarize for you what we've learned. We've learned that mechanical ice sheet forcing alone cannot explain U.S. West Coast LGM hydroclimate shifts. Mechanical forcing can explain these hydroclimate shifts, but only in an uncoupled simulation, on an uncoupled planet without realistic air-sea interactions. As soon as you start to include this mechanical forcing in a coupled simulation, you basically get the opposite hydroclimate response. So there's clearly something not right there. In contrast, it really does seem like it's the coupled climate response to direct thermodynamic ice sheet forcing that's essential in driving the most realistic response on a coupled planet with realistic air-sea interactions and realistic ocean dynamics. But now we're back to the same question that we had before. Why? What is it about air-sea coupling that completely overwhelms the mechanical response to ice sheet forcing in the atmosphere and leads to the opposite hydroclimatic shift on the west coast of North America? What is it about air-sea coupling and its response to direct thermodynamic ice sheet forcing that leads to that much more realistic southward shift in the jet and the proper west coast hydroclimatic conditions that are supported by proxy reconstructions? And to answer that question, we're going to think about how the ocean and the atmosphere interact, and that's primarily through sea surface temperature. Here are annual mean SST anomalies in the ensemble mean of the PMIP3 archive, as well as the LGM full simulation in our CSM1 set of experiments. Both of them show cooling throughout the North Pacific, but they also show a maximum cooling about 45 degrees north along the Kuroshio extension. And you'll notice that this increases the meridional temperature gradient from the equator to about 45 degrees north, and we might expect that to drive an acceleration of the westerlies in the mid-latitudes because of thermal wind adjustment to that SST gradient. And that would be consistent with what we saw earlier, right? We saw that southward shift in the jet stream due to a deceleration of the westerlies north of 45, but also an acceleration of the westerlies south of 45 degrees north. So this SST pattern may be contributing to that acceleration of the westerlies in this portion of the North Pacific. How does this LGM full SST pattern compare to our single forcing simulations? Well, in the Green Mountain simulation, we see a very different SST pattern. We actually see a warming of the subpolar North Pacific and only moderate cooling throughout the tropics. And what that does is it ends up decreasing the strength of the meridional temperature gradient throughout the North Pacific, which would tend to decelerate the westerlies due to the same thermal wind argument throughout the atmospheric column. And that's exactly what we saw before as well, right? We saw that deceleration of the westerlies driven by mechanical topographical forcing in the subpolar parts of the North Pacific. But south of about 45 degrees north, we saw that that broad deceleration of the North Pacific westerlies that led to that opposite hydroclimate response. But looking at the White Mountain simulation, we see an SST pattern that compares very well to the LGM full case once again. So we see that same cooling throughout the Kuroshio extension, an increase in the meridional temperature gradient, and this would tend to support this southward shift of the North Pacific jet and that acceleration of the westerlies on the southern flank of the North Pacific jet stream. So why do we get this SST pattern? It turns out answering that question is a little bit complicated, and it's because, as I keep saying, we live in a coupled system, right? How do we know whether these SST patterns are a source or a symptom of the large-scale atmospheric response to these different ice sheet characteristics? And this is kind of the flow chart that we want to follow when we're thinking about the coupled climate response to, say, thermodynamic ice sheet forcing, right? There's going to be some large-scale thermodynamic ice sheet forcing, and the atmosphere is going to adjust to that forcing, which will imprint itself on the ocean. There will be some oceanic adjustment to that response to thermodynamic ice sheet forcing, and we'll see that as an SST pattern. And then at some point, the atmosphere will start to come into some sort of equilibrium with the ocean. The ocean will couple back to the atmosphere. It'll cause the atmosphere to adjust, and it'll lead to the overall coupled climate system response that we saw before, that southward jet stream and that north-south dipole in hydroclimate as a result of that jet stream response. And in the earlier part of this presentation, we primarily focused on these two bullet points, right? We've seen this SST pattern here on this slide here, and I'm relating it back to that earlier jet shift that we looked at before, but we really haven't quite isolated the direct atmospheric response to thermodynamic ice sheet forcing. We haven't quite found that smoking gun where we see the atmospheric circulation response in direct response to this thermodynamic ice sheet forcing, which will then, imprint itself on the ocean for the first time before the ocean has a chance to couple back and also impact what's going on in the atmosphere. So the way we're going to do that is by looking at our simulations in specific seasons. For example, these are summertime average stationary wave patterns in our White Mountain simulation across the different ocean configurations. And if you're not used to thinking about or looking at stationary wave maps, you can just ignore the contours for now and just focus on the shading. The shading are stationary waves at 850 millibars, so sort of lower in the atmosphere. And you can think about the blues as sort of low pressure and the reds as high pressure. And basically what you'll see is that regardless of the different ocean configurations, you see this low pressure center that at lower levels throughout the North Pacific. And this is giving you a cyclonic circulation that would tend to decelerate the westerlies north of 40 degrees and accelerate the westerlies south of 40 degrees, consistent with that southward shift in the jet stream that we were discussing before. And what's interesting about this is that regardless of the ocean configuration, so regardless of whether the ocean exists in any of these simulations, you get a very similar atmospheric circulation response. So what that suggests is that in the summertime, in this simulation, the large-scale atmospheric circulation is mostly uncoupled. It's largely uncoupled from the underlying ocean. So in the summertime, even in our dynamical ocean model simulation, or even in our slab ocean model simulation where we have realistic air-sea coupling, we're seeing a much more direct atmospheric response to that thermodynamic ice sheet forcing. We can use this information, right? We can leverage this relationship in the summertime to see how the direct atmospheric response to thermodynamic ice sheet forcing is first imprinting itself on the summertime ocean, creating an SST pattern that will persist, hopefully, to the wintertime before it can couple back to the atmosphere and influence the wintertime North Pacific jet stream and then ultimately leading to that hydroclimate response along the U.S. West Coast. So in the paper, we go through a detailed mixed layer heat budget to discuss how the SST pattern throughout the North Pacific arises in our White Mountain simulation, how you get that cooling along the Kuroshio extension. And I don't have time to go through every detail of the mixed layer heat budget, but what I will pull out for you is the most important component of that heat budget, or the most important physical process that led to that SST pattern, was related to changes in shortwave radiation. So here are SST anomalies implied by the changes in that shortwave radiation. This is for the White Mountain Dynamical Ocean Model experiment. The top left is showing you the SST anomaly driven by the full change in shortwave radiative forcing. It gives you this cooling throughout the North Pacific, and particularly along the Kuroshio extension, very similar to what we saw before. You can break this down into a component that is driven by changes in clouds and a component that's driven by changes in clear sky radiative forcing. And we can see that most of the change is coming from changes in clouds, specifically marine stratocumulus clouds, or low clouds, which tend to be pervasive in the North Pacific during the summertime. But again, this is a coupled system, and we know that low clouds and SST are very highly coupled in the North Pacific. Specifically, increasing low clouds tends to decrease SST, which stabilizes the lower boundary of the atmosphere and makes it more conducive to creating low clouds. And this creates a positive feedback that we call low cloud SST feedback. So how do we know, definitively, that the change in low clouds that are implied by this cloud radiative forcing are a direct atmospheric response to thermodynamic ice sheet forcing, as opposed to a response or an adjustment to that SST pattern? Well, we can get to that answer by looking at our White Mountain AGCM simulation. These are the SST anomalies that are implied by the shortwave radiative forcing changes that we see in our White Mountain AGCM run. And basically what you see is a pattern that is very similar to our White Mountain Dynamical Ocean Model simulation. We see a cooling throughout the Kuroshio extension, or an implied cooling throughout the Kuroshio extension that, as I'll show you in a second, is due to an increase in a low cloud fraction. And because it exists in our uncoupled simulation, we know for sure that this is a direct response to thermodynamic ice sheet forcing. With the difference in magnitude between these anomalies sort of further highlighting, the importance of air-sea interactions, the importance of that low cloud SST feedback, which would tend to amplify both the SST response and the low cloud response in the dynamical ocean run relative to the AGCM run. So how do we link these back to changes in low clouds? Well, we can average low cloud fraction in this box for each of these simulations, and that's what we'll see here. And this is as a function of month in our simulations, and I think this is really cool. Basically, what it shows is that in the AGCM case, in our White Mountain AGCM simulation, you can see that there is about a 20% or a 15 to 20% increase in low cloud fraction in the summertime. And that's when we expect the largest thermodynamic response to ice sheets anyway, because we get the most insulation to reflect in the summertime. And you see a very similar response in the White Mountain dynamical ocean model simulation, with the difference, once again, further highlighting that low cloud SST feedback that exists in the dynamical ocean run but doesn't exist in the AGCM run. So sort of in summary here, the direct atmospheric response to thermodynamic ice sheet forcing in the summertime is to produce low clouds, or an increase in low clouds over the North Pacific, which is cooling SSTs. Just wrapping up, this is a schematic illustrating the full coupled climate system response to a tall and bright ice sheet, so both mechanical and thermodynamic ice sheet forcing. In the summertime, we get lots of insulation, which is being reflected out to space because of the high albedo of the ice sheet. This creates a strong diabatic heating anomaly over the ice sheet and creates a stationary wave response over the North Pacific, which we see as this low-level cyclonic circulation. This would tend to drive cold air advection at low levels over the western North Pacific from the high latitudes, and then increase moisture transport from the tropics over the eastern North Pacific. So the combination of cold air advection and increased moisture would tend to lead to the increase in marine stratocumulus clouds, which decreases insulation at the surface, causing SSTs to cool. So as the SSTs continue to cool, that stabilizes the atmospheric boundary even further increasing the formation of low clouds, which further decreases the SSTs. So that's that low cloud SST feedback we had discussed previously, and that helps these SSTs persist from the summer into the winter, where the increase in the meridional temperature gradient from the equator to about 45 degrees north helps helps drive an acceleration of the westerlies throughout the atmospheric column, particularly south of about 45 degrees north. And it's this acceleration of the westerlies that helps reinforce a tendency for mechanically forced shift in the North Pacific jet, all told ultimately leading to this north-south dipole and hydroclimate that we see in proxy reconstructions. I really appreciate your attention. I'll just leave off by mentioning one more time that we have a postdoc opportunity available to continue some of this work, looking at these runs in further detail. Please email me if you're interested, or if you know somebody that might be interested. Otherwise, our paper is published in Earth and Planetary Science Letters, so feel free to check it out. Thank you for your attention.